So, well, in this presentation, we will discuss a real-world scenario where we apply the novel approach of autonomous performance optimization in order to reduce the AWS infrastructure cost of operating an Apache Spark batch application, while at the same time increasing the performance in execution time. The target of this optimization is a business intelligence application that operates in the digital media industry that analyze the user data of their customer in order to get KPIs such as click-through rates of the suggested contents, the user attention, user engagement, and in fact to analyze such volume of data, this is implemented as a Spark application, which runs on a cluster in the cloud. And okay, next slide. So the goal of our optimization of this initiative is to find the right size for this cluster, the right size for the volume of data we are going to face, in order to minimize the costs related to operate this infrastructure. And the knobs we are going to operate on are, first of all, the size of the cluster, of course, namely the number of instances, and also the size of the instances that takes part of this cluster, and also finding the right Spark parameters that allow us to get the best performance, the best execution time for the specific given cluster we are trying. And usually the challenges that we have when tuning Apache Spark is the volume of data we have to face, and also the fact that the performance can greatly when the volume of data change, because maybe we have different environments with different characteristics, or maybe for the same environment, the volume of data may change as your business grows. And the problem is that this kind of the optimization of this cluster is a manual work because it requires to test several configurations manually, and it's something that we are really looking into to minimize the human effort. Okay, next slide. With the next slide, we want to give you, first of all, quick overview of what is Apache Spark, since some of the performance people here might not really be familiar with this specific framework. So Apache Spark is an open source distributed computing framework for big data processing. Its core concept is based on distributing the data, splitting into different partitions and distribute it on the cluster, and then have a driver program which builds the graph of the computation needs to be made to get the desired results, and then orchestrate a swarm of executor processes that are scattered across this cluster, and assign the tasks that need to perform to those executors in order to analyze the data in a distributed fashion. And this relies on a cluster manager, which is in our case is Hadoop Yarn, which takes care of managing and distributing the resources to the said executor processes. The next slide. We have Apache Spark is a challenging beast to tune because there are no really universal rules that allows us to find the best configuration on any given cluster on any environment. Because it's all boils down, the configuration depends on our application, on the underlying architecture, and how this application moves the data around. We have problem with when tuning Spark, that it's highly sensitive to the data set and how it is distributed. In fact, changing for example, changing how the data is partitioned, the dimension on which those data are partitioned, can dramatically change the performance of the application. We also often have the situation where the data that is used in the development phase does not really mirror how the data on the production environment, or maybe we have a different production environment with different characteristics. And as already said, the data on the same environment may change over time. And then we have to take also into account the changes in the code. So we might find ourselves in a situation where the previous configuration of the environment may not be up to the task anymore, and need to repeat the tuning process several times. And there are also this classical situation where the default Spark parameter are more designed for development purposes and are not really suggested for production environments. So several big data vendors provide us with suggestion and best practice on how best to tune our application. But again, it really boils down to our application and our data. So there is no magic rule. So if we are able to really find the best configuration depending on our application and our data, we can get really significant improvements in the performance of our batch jobs. And okay, next slide, thank you. And another major hurdle in tuning Spark is the sheer number of parameters that are available. We have the parameter that our custom application may expose. Then we have also the Apache Spark framework and Hadoop that together expose more than several hundred of parameters, which is a really high number of parameters for the traditional performance engineer to wrap his head around. Then also we have, if we want to dig also in the lower layer of the stack, we can get also to the underlying Java virtual machine or the operating system level, with probably most of the people here are really familiar with all the complexities of tuning, fine-tuning those levels. And moreover, all these parameters are really tied together, because you can really hope to change one of those parameters without impacting all the others. So any change must require to change several parameters accordingly. So this is a very complex scenario for the performance engineering point of view, because it touches several areas of expertise on a lot of different layers. And next slide, thank you. There was supposed to be some animation in here. Then we have another layer of complexity, which is the cloud. Usually, all the Spark application run on in-house shared clusters, on-premise cluster. But today, new cloud providers are offering new appealing pay-as-you-go solution that allows the companies to be more agile and more cost-effective. In particular, you can think about just provision your own cloud infrastructure, scale it up or down depending on your current computational need. You can even get to the extreme where you provision a cluster just for the execution of your specific job according to the resources that specific job needs, and then just get rid of the cluster once you are done. And you don't even have to worry about the other applications that might run on the same cluster and that are going to steal your resources. So this is really handy, but that gives us even more parameters that we have to throw in the bin, more parameters that we have to tune. For example, we have to get the right number of instances, decide how big they are going to be and their family. For example, if you right now on Amazon EMR, when building a cluster, you have at your disposal more than 100 different possible configuration between a big cluster, small one, general purpose, compute optimized, memory optimized, and all these classes have different characteristics, different performance characteristics, and everything has to be weighted by its respective cost. So we can say that big data cloud provided services are undoubtedly a game changer, but it allows for companies to be more cost effective and be more agile, but maybe we are still leaving some money on the table. Next slide, thank you. And so to squeeze the best performance out of a cluster, nothing beats the actual testing the whole stack to get empirical data of how our application behaves on different configuration. But this is still an extremely time-consuming task that requires to run the same application with different configuration over and over again. This is a job that is a manual task, is extremely repetitive and sometimes, why not, even boring. So we might even have to repeat the same process for different customers, different environments in an endless loop. So we really want to be more effective to find a better trade-off between having suboptimal configurations in our cluster because of configuration that does not really get the most of our resources, and or just having to allocate our engineering team to perform those manual tasks. So next slide, please. Our solution is to use the novel approach of the autonomous performance optimization to scale up the tuning process to a higher level, allowing us to fully automate the tuning process in order to remove the human element from the loop. And to do that, we are trying to leverage key elements such as machine learning and automation. Machine learning these days needs no introduction. It allows us to analyze a volume of data that were previously impossible to think about. It allows us to have a machine learning process that is able to analyze, in our case, the performance data, and in order to correlate those metrics to the parameters we are going to tune, correlate those metrics to the parameter across the whole stack in a way that is really challenging for the traditional performance engineer made of flesh and bone, thus driving the whole process. And as any other machine learning process, the key element is data. We need to gather a lot of data, which means that we have to run several performance tests. And so the other key element, automation, thanks to the modern DevOps tool, allows us to fully automate the whole process of performing the test, starting from the configuration of the environment, provisioning of the environment, to the actual execution of the performance test and gathering of the metrics. So putting all this together, we can have machine learning, this optimization engine that orchestrate at the high level the entire process, analyzing the metrics, the metrics data, generate candidate configuration, a promising candidate configuration to test, passing down those parameters to the workflow. That, for example, in our case, it will forward those parameters to the pipeline that takes care of provisioning our cluster, and then configure the monitoring tools, and then run the actual execution test using the Spark parameters, again suggested from the engine, and then gather all the metrics and forward back it to the optimization engine in order to analyze those data, updates the model of the tuned environment, and then suggest again a new promising configuration to tune according to what is our goal, which is in our case minimize the costs. And the whole process, has to be fully automated from the selection of the parameters to the actual execution of the test. So next slide, please. Yeah, we have some cool animations. And jumping back to our use case, which, as we said, is a real-world application that we tuned. We have this Spark component, which is part of a broader framework, this warehousing solution that analyzes the KPIs, the performance of digital services, analyzing, gathering the raw data generated by the user actions, such as browsing catalog, browsing content, performing text searches, bookmarking contents, financial transactions, in order to get the KPIs for that allows us the marketing team to understand how the business is going. It in our case, it generates 1 million daily visits with 25 million daily raw events, and also generating 15 gigabytes of data. And we have this cluster on Apache Spark that runs on Amazon Elastic MapReduce service, running on 4 different instances. For those who are familiar, those instances are 4 large instances. Next slide, please. Thank you. So our goal is to minimize the monthly cost of managing such application, namely minimizing the bill that we are going to get at the end of the month. And we can achieve these results in 2 ways, which is either speeding up the application, reducing the uptime of the cluster, because this is an ephemeral cluster which is provisioned at the beginning of the execution of this application and then destroyed once we are done. This is it runs multiple times a day to update those KPIs. And the other solution is to try to shrink the size of this cluster, finding also a new Spark configuration that is able to complete successfully under those with that specific cluster. Then we have to respect some constraints, and the application can take too much time because we don't want the execution to run in the next schedule one. And we are letting this optimization engine understand by its own which is the best way to minimize this cost. Okay, next slide, thank you. So we are going to tune the parameters we are going to tune in this case are the number of executors, namely the number of the process that crunch the different partition of data in a parallel fashion, the number of executors, the number of CPUs and the memory allocated to every single executor. We are going also to tune the CPUs and the memory for the driver program, which is the one that orchestrates the executors. The level of parallelism, which is the number of partitions the data set is going to be split into. And we're going to tune also the number of instances in this cluster and also their size, and also the size of the master node. As I already mentioned before, all those parameters are already tied together. So one change in one of these parameters would probably require cascade through the other one, requiring to, the whole set of parameters has to be updated as a whole. And then in the next slide, we can see that performing some preliminary analysis of this application, we realized that there are some bottlenecks in this application, meaning that because of some imbalances in the distribution of the data, the application was not really taking advantage of the full parallelism of the resources. Because of this imbalance in the distribution of data, or the computational load was concentrated in a few executors of the 11 available, making so that basically most of the cluster was basically waiting for the completion of those bottlenecks in this architecture. And so one caveat is we are not going to, this is something that has to be addressed at the code level, modifying how the data is distributed, how it is moved around the cluster. But this is outside the scope of our optimization. We are not only going to tune, as we say, the parameters. We don't want to customize the application for this specific customer, for this specific environment. So we want to try to find the best configuration that is able to take into consideration these bottlenecks, and then get the overall best performance from this cluster. Next. Thank you. Next again. So on this graph, we can see how this optimization behaved. We can see that in this graph, every blue dot represents a tested configuration. We performed 15 different tests on 15 different configurations for overall runtime of almost 4 days. And the dots that you are seeing here are the relative scores of the performed tests. We let the application run and then compute the cost that we will have at the end of the month using that specific configuration. And then this value was then normalized by the value of the baseline, which you can see in red as a reference. The baseline metric, cost metric, is an estimated price of $1,400 a month. So that is the value that we're going to beat. And in green, the green area is as a reference is the best configuration, is the value of the configuration best configuration found so far. And you can see also in yellow a placeholder for the failed execution for those configurations that were not able to complete successfully or even start in the first place. Then we have letting the optimization run. We have an initial phase where this reinforced learning algorithm sampled for the initial phase, the space of the configuration, trying to get an idea of how this configuration behaves. This was performed for the first 10 executors. That gets underlined if you proceed with the presentation. And then we switch to the actual optimization phase, where once the engine has enough data, it starts trying to guess what are the promising configuration and then test it and get back the feedback of how it behaved, and then update its internal model of the application in order to iteratively try new configuration based on the previous data. We can see that initially we were able to get good result from the beginning. This was because the cluster was already over provisioned in the first place. That's something that we suspected from the beginning. But also then after around 27 iteration, the engine was able to nail a configuration that was able to complete successfully on a cluster whose size was significantly smaller than the baseline one, moving from around 35% in the of saving to almost 50%. So we were able to we let it optimize even further, achieving a final reduction in the price of the cost of the cluster of 52%. Okay, next. Oh yes, among the honorable mention, we were also able to execution time for some application by the 20%. And so how did the engine achieve these results? So basically, what the engine understood is that the master node, which is the one that holds some basic Spark processes, was over provisioned for its use. So it was able to move from was able to understand that the cluster is good even with an instance that is much smaller than the original one, a quarter with respect to the original one. But what's really interesting is that we were able to move from a cluster of three different executor nodes to a single one with which was only double the size of one of the single one in the previous cluster, moving from three different 4x large instances to a single 8x large, which allows us to have a significant saving on the 44% of the allocated resource. What's also interesting is that we moved from an initial number of 11 different executors to just 3. And this is really puzzling because Spark is supposed to be to take advantage of massively parallel computation. So that's really unusual. So in the next slide, we can see the reason for that. As we already said before, in the analyzed data, we were able to identify those stages in the application, as we already highlighted before, with a very small level of parallelism where most of the CPUs were idle. So Spark, this optimization engine, was able to understand that overall the application didn't need such level of parallelism because most of the executors were idle for most of the time. You can see in this graph where the orange line is the baseline and the green one is the average used CPUs during the execution of the test for the best configuration. And so the engine was able to identify that all those executors were not really doing useful work, so it was better to have less executors and slightly increase the CPUs allocated to the one that were actually working, moving from this way from 11 executors with 3 CPUs to just 3 executors with 5 CPUs. And this way it was able to try to speed up this bottleneck, slightly speed up this bottleneck, but at the same time having less resources, less executors. We were able to both allocated less resources, having a smaller cluster, and also reducing the execution time of the overall application, because as we see here in this graph, the application takes around 10% less time to complete. So we were able to achieve this overall 52 gain in our AWS build. Okay, next slide. As a side note, we were also able to reduce significantly the execution of the allocated memory, which is that gives us some more margin when the data set increase. Also, this factor of having all the executors concentrated on a single instance allows us to speed up the application in order to let's say, because of the when moving around the data across the executors, this is performed locally instead of transmitting the data on the network, thus reducing further the stall time of those executor processes. Okay, last slide. So what are the takeaways? Is that tuning Spark is not trivial, and we have a huge amount of parameters that are tightly related among themselves, and there is no really optimal magic rule to get the optimal configuration for any cluster. It boils down to our application and our resources. Then we also have understood that because out there are maybe there are a lot of applications that are not really taking full advantage of their allocation of their resources. There is a lot of untapped potential because the configuration performed based on the assumption that does not really reflect the actual production environment. And we also learned that cloud solutions are not necessarily cheaper. They are flexible, they are more convenient, but sometimes it becomes tempting to just throw resources at the problem. But if our cluster, if our application is not really able to take advantage of those resources, we are just wasting money. And finally, thanks to artificial intelligence and autonomous performance optimization, we can have an extremely powerful tool at our sides in a way that it was not analyze those parameters and tune application to a level that was not possible before, thanks to the huge amount of data we are able to analyze. And also thanks to automation, we are able to unload the burden of performing the manual work from the performance engineer, so that he is able to focus on higher level activities. Because as we can see in the application we tuned, during the 4 days of execution of this optimization, basically no performance engineer was performed in this process. It was fully automated, and so we were just, let's say, watch the magic happens by its own. That's it. Sorry for the initial delay. I had to be quicker than originally intended.
No
So if you
worries.
have any questions.
Let me stop sharing my screen. Get it back to here. All right. Let me stop the sharing the screen. Up. Here it is. And I'm going to enable the various pack members that are still connected. Oh, I can see that we have a lot of speakers from the next region that is connected. So I'm going to enable the various webcams. I don't know. Alejandro was connected this morning, but I think he's busy. So I enabled, but I may not be able to talk. But let's try. Oh no, so he's not. He's not. So I'm not going to disable him. All right. So first of all, thank you. I'm gonna maybe turn off Joey's webcam. So first of all, thank you, Luca. My question would be, at the beginning of the slides, you mentioned that there were 200 parameters for Spark, 200 for Hadoop, 100 for the operating systems, 800 for the JVM, and I don't remember the other one, but the application then.
Yeah.
In this simulation, how many parameters were involved to get those impressive results? Did you only touch the Spark settings, or did you also touch OS operating system plus I don't know other?
Yes, in this case, we tuned 10-ish parameters. As we said, 3 for the to size the cluster, and the other 7 parameters were Spark parameters. And we can even think this approach allows us to be full stack, because we can just throw in the mix even more parameters. Say one thing we wanted to try in further development of this use case is also tuned the JVM parameters, for example. But of course, the more parameter you add, of course, the number of dimensions we have to explore, of course, increase. But with this approach, we can also have pretty good results, also pretty quickly, if you think about it, obtaining those results in just 4 days. That was quite a feat. And yes, but if we want, we can scale up the number of parameters as we want. Of course, it's going to be slightly more complex, but yes, of course.
And then the last question I have from my end is, so it seems that from the run 35, I think it started to have a 40% reduce of the cost or to reach the target. And what are the between the simulation 35 and the simulation where you have observed a 52%? Was it the same settings, or was it was there a major change? Because when you look at the graph, it was like almost not flat, but sort of.
Yes.
I was wondering, was it several runs to confirm that run 35 was the best one, or was it completely different result?
Yeah, there was not that mind-blowing changes in those configuration. Mostly was just further refining that configuration, because we had this initial phase where there was around 35%. We had this jump between the 35 and 49%, where he was able to try successfully a significantly smaller cluster, because in the previous configuration, basically, it was trying, if I remember correctly, it was a 12x large instance, and so most of the gains was because of the reduction in the execution time. because the size of the cluster was roughly equivalent to the baseline, because it was 3 different 4x large, and we had one single 12x large, which is they are basically from the number of CPU and the number of overall memory, they were equivalent. But finally, when on the 27th experiment, he was able to nail this configuration that was able to finish complete successfully using just a 8x large, which led to a further increase and decrease in the allocated resources and also in the costs. And then we let it just try to further refine to the final 52%, hoping to get even better results.
Okay, that's it. Thanks. I mean, that was pretty interesting. I think there is a lot of things. I'm having a detailed blog that would be pretty awesome. So, Luca, if you have the time to write a blog and share it, that will be just wonderful, because I think there's a lot of things to go deeper in the results that you had Camara discovered. So that I think that will be quite beneficial for everyone. Todd.
Yes, unfortunately, I had to cut something from the speech, but yes, of course, maybe hopefully in the blog we don't have the same technical issues.
So Todd, how are you? So do you have any questions for Luca? Oh, I don't hear you. The mic. Hello? Nope. Nope. No sound. I don't hear you. I don't know if you have selected the right mic. I said the last session of the Europe is the moment where we all have all those technical issues. That happens once in the evening. I hope so. Cross fingers. No, I'm still not able to hear you, Todd. Maybe you can, if you have questions while you're resolving your mic issue, maybe you can drop the questions in the Q&A or in the chat.
Yeah.
Otherwise, I'm looking at the watch. It's almost, for me, it's the pizza time. It's time to get some food in the stomach before we can start with the next region. So, Todd, if you're not able to resolve it, I suggest that we conclude the Europe region. Oh, so you dropped the questions. All right. Not working. All right. No worries. All right. So if let's resolve the sound issue of Todd during this break. And I would like to thank all the European speakers. So Stain, thank you so much for your presentation. It was really a great session. Andy, again, thanks, because I think the way you split the work between you and Roman was very clever. So I really appreciate that. Thanks to Alan Gordon that presented a right night's topic. By the way, Todd, you should watch to that session. He using Splunk to collect data from production. So that was a pretty great session as well. Thanks for Roman again. I really liked the session, and you highlighted great tools in the demo. So I'd like to thank you for that. And last, Joey, with your framework, that was just wonderful session. And thanks, Luca. Even if we had these technical changes, I think the content was there, and the value for the community was there. So thank you so much.